Alright, welcome back to EC 382. Captain Beyer here. Hopefully you've recovered from Module 13, Part 1. I know it was a lot. Again, just remember, all we're doing with the timer is setting up the settings. And then we're going to use that timer, which is just counting at a certain rate. Then we're going to compare that count value to our goal, which will be our period. And then once that period is hit, we're going to call a function. And that's going to allow us to intermittently, periodically call interrupts. So that's the first way. The second thing we're going to look at now is how would we use this timer with pulse width modulation. So Dr. Beck taught you a lot about motors, taught you the benefits of pulse width modulation, how it's better than some of the other options. But what you then implemented was turn on, wait, off, wait, repeat. And to do that, this wait right here blocks, which is not great because then you can't do anything else. What the timer allows us to do is all that counting is done in the background, and every time, so say I wanted to run the motors, turn them on for 10, off for 10. So in the background, something's happening, someone's counting 2, 3, 4, 5, 6, 7, 8, 9. Motor gets turned on. So let's say it was off first, motor gets turned on, and we go again. 0, 1, 2, 3, 4, 5, 6, 8, 9. Motor turns off. So during this whole time, we can be doing all kinds of other things. 9 hits, interrupt occurs, value, we either go do something or we can take advantage of these output modes that we talked about in the first video, which one of them is toggle reset. So now in the background, without us even having to do anything, we can toggle this pin 2.6. which is going to be connected to timer, and this is how this A0 module 3. This one here is timer A0 module 4. Okay, so and we have to use a different timer, so we can't just use timer A1 module 3, 4, 5, 6 because the pulse width modulation is going to have to happen a lot faster. So our clock is going to have to go a lot faster than our 100 millisecond periodic interrupt. To give you pulse width modulation, we kind of want around 10 milliseconds, right? That's what we've seen. And then our periodic interrupts to check the bumps is 100 milliseconds. So, that's more than enough time. 100 hertz, or sorry, 10 hertz, 10 times per second. That's more than enough time to check the bump sensors, but is not fast enough to update the motors. So 10 milliseconds, it's going to give us 100 hertz, which is what we need to take and interact with the motors. So we're going to use toggle. So I'm not going to go through all the registers like we did last time. You've seen them now. The code. So this is all going to be in the pulse width modulation.c file. And what the Texas Instruments did was provide you an example of this pretty much almost exactly. It's almost a copy and paste, but there are a few things you're going to have to look at. So specifically, which interrupts am I talking about? What duty cycle and pins am I looking at? But they give you an example working on pins 2.4 and 2.3 or something along those lines. That almost looks exactly like what we're doing with 2.6 and 2.7. So basic idea is we are going to have our counter. It's going to count to a certain value. Toggle reset. So we're using toggle reset 010 for our out mode. So let me just add that for you. So that is in this guy here. So toggle reset set out equals 0. what was it? Toggle reset 010. Okay, and then we are going to use count. We're going to do up down count, which for that one we're looking at MC equals 1 1. Right there. Go nice and slow. All right, MC equals 1 1. Okay, so duty cycle, right? So duty cycle is our high over our period. So if we're counting for a certain amount of time, what we can change is how our high value, and that's going to change then our duty cycle. So we're going to keep period constant. Remember, period is constant. So let's move this down here so it follows a flow of sequential down the page. Duty cycle equals high over period, which our period remains constant. But what we can change is how long we're high have an active high or a 1. So how will we do this? The way we're going to do this is we're going to set our CCR0 in our initialization to our period. And if we go back up here and we take a look at our CCR0, what is that? It's going to be our first compare and capture value, but we're going to use it as our period. And the way it works with up down is up down CCR0 is the counts counts to CCR0. Up down counts to CCR0, and we can see that when we say up down mode. I know there's a lot of scrolling going on here. That's why it's always helpful for you to have these printed out so you can just flip through them. But we can see here our mode 1 1 up down mode. Timer counts up to CCR0. So that's our period. And then what's going to happen, so say we set our CCR0 to 10, our counter is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, and so on and so forth. Okay, and we see that here. And what's going to happen then is, and this is where the compare comes in. So it's just going to count up to CCR0 and count down. And then we're going to use CCR3 and CCR4 to establish how long we are high in our signal. So for this example, we're going to count to 7. We go 0, 1, 2, 3, 4, 5, 6, 7. Then we're going to toggle. So from here we were 1, we go down to 0. We're going to stay there until we see a 7 again. We're going to go until we see a 7. We're going to go until we see a 7. We're always going to just go until we see a 7, because that's going to be our compare value. And so you think, okay, that's 7 over 10, 70%. Duty cycle, that's our goal. What we see here, we're active high for 1, 2, 3, 4, 5, 6, 7, and then low for 1, 2, 3. Okay, that's not quite. Well, that is exactly. Sorry, let's start here. Let's just start as if we're here and here. So we're low for 1, 2, 3. Then we're high for 14. and then we're low for 3. So to get our correct duty cycle, what we're doing here is we're using every 2 cycles of this. And that's why we have this 2 right here, is because the way this is working, even though we're low for 1, 2, 3, 4, 5, 6 here, that's 6 counts, we're going to be high for 14 here, so we get 14 over 20, which is equal to 7 over 10, or 70%. Okay, so the way we're going to do this is our CCR0 is going to equal our period, and our CCR3, I think it is going to equal motor 1 duty, or the amount time high, CCR4 motor 2 duty, or the amount high. And to get our 10 millisecond kind of duty cycle, we actually need 20 milliseconds. So to do that, and I'm just gonna do the math here for you already. We're going to need to divide our clock by 8. That's going to get us 666.7 nanoseconds. Okay, so that's the basic concept of pulse width modulation. So basically, the toggle reset. So toggles once it gets to 7, and resets once it gets to our CCR0. Doesn't matter because that's already 0, so it works out great. That's going to give us our duty cycle of 70%. And it's going to toggle the bits for you automatically in the background. So if you want to speed up your motors, you don't have to do anything other than change CCR3 and CCR4. Once you change those values, then you're speeding up or slowing down the left or right motor. And what's cool is you can control each motor separately. So the left motor can go at a duty cycle of 30%, while the right motor might go at 70% to kind of give you a not so sharp left turn. All right, the last thing we need to talk about is period. So we've already seen how this is difficult with the SysTick. Remember that 48 megahertz clock. If we wanted it to do something for 100 or a microsecond, we have to divide that by 48 and then do the clock that way. So every time, and I'm going to update these timers. This is what I like to call like timers now. So these are what our timer's doing. We have timer A0 module 3 and timer A0 module 4 both connected to the motors. They're doing output compare. This is doing output compare as well, but a little bit different. More compare, less output. We're going to take the SMCLK, which is at 12 megahertz. Remember, that's 48. That's your system clock divided by 4, so 12 megahertz. We're going to divide it by 8. That's going to get 666.7 nanoseconds. But if we want our motors to have a period of 10 milliseconds, we're going to have to provide a period of 15,000, because our clock, every time it counts, it's counting at a rate of 666.7 nanoseconds. So 0, 1, 2, 3. Pretend like I could count at 666.7 nanoseconds. If I multiply that by 15,000, I get about 10 milliseconds, which gives us 100 hertz. So, 1 over 10 milliseconds, 100 hertz. Okay, but if we want to run our bump sensors at a 10 hertz or 100 milliseconds, that clock is going at a different rate because that's timer A1 module 0. We divided that one by 24, giving us a precision of 2 microseconds. We take 2 microseconds, multiply that by 50,000. That's going to give us our 100 millisecond. So when we do our timer A1 init, we have to put our function, and then the frequency we want it period, which is going to be 50,000. So things I will definitely test you on: changing this number, changing this number. The registers aren't as important. I do want you to understand these here, which interrupts, am I going to be running my cystic handler interrupt when I'm calling my timer A1? No, I'm running my timer A1 0 IRQ handler. Same thing with our pulse width modulation. So just hopefully you get a basic understanding of this stuff. We're going to implement it. We're going to see it in action, and you're going to see how this is a much better option than just sitting around waiting for cystic to count.